Good afternoon, everyone, and thank you for all sticking around to hear our presentation. My name is Julia Weiss, and I'm the Vice President of the Michigan Aeronautical Science Association, and we are a project team on campus that designs and builds amateur rockets. So here with me are my teammates Jack, Akhil, Paige, and Alfonso. And today we are presenting our current rocket called the Tangerine space machine that will launch Michigan into space. So we are competing in the Base 11 Space Challenge for a $1 million prize. We are building and testing a 1,400-pound rocket, and we are planning to launch the Tangerine space machine, which we refer to as TSM, in May 2021. So TSM stands 27 feet tall and 14.5 inches wide. The engine uses RP1 fuel and liquid oxygen oxidizer. It effectively produces over 4,000 pounds of thrust, and it has a specific impulse of 211 seconds. Our team is comprised of 6 sub-teams: Aerodynamics and Recovery, Structures, Propulsion, Avionics, Production, and Assembly, Test, and Launch Operations. The image above illustrates the main components of the rocket, and the sub-teams work on these components, and ultimate integration will lead MASA to a successful launch. So now Jack, our chief engineer, will discuss our work on aerodynamics and recovery.
Yeah, so the aerodynamics and recovery subteam is primarily responsible for simulating the aerodynamic forces during flight and for also designing the recovery system, as the name implies. So on the bottom of the screen here, you could see a 3-degree freedom flight simulation. With these simulations, we were able to determine the rocket's max altitude, its bending moment, maximum dynamic pressure, and a bunch of other things. So that's a 3-degree freedom flight simulation. We are also currently developing our own in-house 6-degree flight simulator in MATLAB. Also on the screen, the top picture shows our nose cone and some safety we did on it. So the burnout velocity of our rocket is Mach 5.5, so the skin is obviously getting quite hot. We found that through these transient thermal simulations that the entire body reaches around 500 degrees Fahrenheit, with the tip reaching a temperature of 1,500 degrees. So as a result, we'll be using a titanium tip nose cone to prevent it from melting. Over the past year, the team has also made significant progress on fin design. So the fins on the rocket are used to provide for passive stabilization. We don't have any active stabilization. So the fins we design, or the fin design we have chosen is a 3-foot long trapezoidal fin. We want this design because it's easily manufacturable and it uses a continuous panel from the fin to the rocket body. So on that right there, you can see the render. That's all one piece that's bolted at the fin edge. But one of the largest problems designing fins is preventing flutter, which is essentially a high amplitude vibration. So on the left, you could see a picture of a ANSYS simulation that we used to predict the deformation of the fin due to flutter. The prototype, also pictured in the center there, was a small scale model that it was very useful for teaching us about the sheet metal manufacturing we'll have to conduct to build the actual full scale fins. And then, as I said, on the right is a current render of the fin model. And then once the rocket goes up, we obviously want to be able to get it back down in one piece, hopefully. So that's where the recovery system comes in. So on the left, we have our separation mechanism, which sits at the top of the rocket and connects the nose cone to the rest of the rocket body. At apogee, a command is sent from our engine controller that will separate the nose cone using a ball lock pin pneumatic mechanism. And then that will essentially release a pilot chute that will also allow the SEDS payload that we were talking about before, the BX-4, to be shown in space and released kind of into space. And then once all that happens and the rocket re-enters, there'll be a drogue parachute, or excuse me, a reefed parachute, which essentially acts as a drogue. So there's that reefing line that you can see over there that will kind of prevent the rocket from being fully inflated, or the parachute from being fully inflated. And then at a lower altitude, this reefed line is cut, and the full diameter of the parachute is inflated to 50 feet. And then this whole mechanism, as I said, is triggered by avionics, which is primarily a GPS and barometric data. And that's the recovery system. So now it is back to Julia for structures.
So the structure subteam designs, builds, and tests the structural frame and components of the rocket. The main components include the tanks, end caps, airframe sections, raceway, and thrust transfer structure. Shown on the left is the inner tank bay. Its main objectives are to structurally join the 2 propellant tanks and to provide a smooth aerodynamic transition between them, and to provide space for plumbing and avionics, which is why we have the panels incorporated. The end caps were designed to withstand the pressure of propellants, aerodynamic stresses, and thermal stresses. we performed a simulation of an end cap under thermal and static pressure loads seen in the center image, and we found that the largest stress concentration is less than the yield stress of the aluminum, and therefore our results indicate that the end cap will most likely withstand the loads acting on it. And the image on the right shows how the end cap and airframe section will be assembled together. So the raceway runs along the outside of the rocket, and a cross section is shown in the top left, and you can see the tubes for plumbing and avionics. We are currently studying the thermal and aerodynamic effects on the raceway in order to ensure its stability. At the moment, we are considering two thrust transfer structure designs. The purpose of the thrust transfer structure is to structurally attach the engine to the rocket and effectively transfer the thrust produced to the rest of the rocket. So through running simulations, we will determine which design produces the minimal stress for the minimal weight. And over the summer, we will finalize this design and begin manufacturing. One of the main accomplishments of the structures team this past semester was performing a burst test. And the purpose of this test is to validate the predicted burst pressure of our propellant tanks. So we got tanks and end caps manufactured, and then we filled the tank and slowly increased the pressure inside until it burst. And you can see in this video clip, the tank actually bursting. And on the right is the brittle weld fracture in the tank. So we found that the maximum pressure the tank can withstand is 575 PSI, which is slightly below what we expected. So this upcoming semester, we will perform another burst test to check our results. And this upcoming year, Structures has a lot of manufacturing and testing that will occur to improve our components and prepare us for launch. So now Akhil, our treasurer, will go over the propulsion subteam.
All right, so this past year, the propulsion subteam has been simultaneously working on the design of our new flight engine and the testing of our previous engine, PT-163, which can be seen in the top row of images. The engine consists of three major components: the injector, the combustion chamber, and the nozzle. In addition, the subteam also designs both propellant valves. In the bottom right of the slides, we can see a picture of the components of the liquid oxygen valve. To the left of that is a picture of the LOX valve during a test with PT-163. PT-163 is our LOX ethanol engine, which we developed to further our understanding of fully liquid systems and help uncover any new concerns. All of the testing of PT-163 is conducted through a joint effort led by ATLO and the propulsion subteams. All right, so here we have a more detailed view on the components currently being designed for our LOX RP1 engine. The CAD cross sections displayed are of the full engine assembly, the injector, and the LOX valve. Labeled with arrows are the fluid flow paths through the engine assembly. The cold RP1, which is shown in the red arrows, will flow up the chamber walls and absorb heat from the hot wall, decreasing the overall wall temperature. This is what makes the engine regeneratively cooled. To ensure the validity of our CAD designs, we conduct simulations with both finite element analysis and computational fluid dynamics. On the right, we have results of FEA on prior injector and engine iterations. These specific simulations were performed to estimate the max stresses under loading conditions. Both of these simulations showed that our designs met an acceptable safety factor near 2.3. In the summer, we will be finalizing the component designs and running similar simulations to estimate an accurate pressure budget and determine safety factors. We will be preparing to machine the required components and perform static test fires of the new engine in the coming year. Next, Paige, our social lead, will talk about the Avionics subteam and its work.
Hi, so Avionics works with the electronics for Tangerine Space Machine to make things go, being responsible for controlling the different valves and motors on the rocket and ground systems, as well as the different sensors for reading the pressures and temperatures at various points on the rocket. Some of the projects that Avionics has been working on during the last year include the system needed in order to conduct our tests, as well as the system for maintaining pressures in our propellant tanks as the propellant drains out. These avionics systems were what allowed us to conduct our hot fire and our burst test, as well as collect valuable data from it. See, in addition to making things go, Avionics has the responsibility of collecting the information about what's going on in the system as things occur. In our testing campaign so far, it's been about reading sensors for pressure and temperature, as well as the thrust of the engine. But in the future, it will extend to GPS tracking, altitude confirmation, and sending down the telemetry for TSM when we launch. The avionics also has to be smart enough to read the systems of the rocket and understand when it has to trigger an abort. Many members have been working to determine the different ways that these aborts can happen, depending on the failure mode of the rocket. So here on the slide, we have two architectural layouts for different control boards and the systems of TSM. We'll start at mission control where we'll be at, far away during the launch. And as we communicate with the rocket, it will tell us things about its location and some necessary sensor readings. On the rocket itself, we will have the flight computer, which will talk to the various boards that control the different parts of the rocket, such as the engine, separation mechanism, and the pressurization system. These things need to be powered, and that's controlled by our power board, and we also need to be able to save data to our black box system. Avionics has experienced a ton of growth during this project as compared to years past, as can be seen in our diagram on the right here, our evolution of the engine controller. Because as the scale of what we want to do increases, the need for more complexity of the avionics also increases. Now I'd like to say a few words about our production subteam. So the production subteam is a crucial one to the team, as they are responsible for the actual fabrication of many of our components. As a result, the work here is obviously extremely hands-on. And the photos here are some of the components the machine for the project since we've begun, like our main propellant valve on the left, and on the top right, we have our tank end cap, basically a giant cereal bowl. But there's a lot of time, skill, and knowledge that our team members get to develop in order to be able to interpret the drawings of components and actually machine the parts to make the ideas of our team a reality. Many of our crucial systems are actually designed and manufactured completely by students and are in-house at the Wilson Student Team Project Center on North Campus. In the next year, now that the bulk of the designing is almost done, the production subteam will be in charge of a lot of the manufacturing of our components before their testing phase. Related to that, I'd like to introduce the ATLO lead, Alfonso, to talk about ATLO.
The Assembly, Test, and Launch Operations Team, or ATLO for short, is responsible for designing ground equipment, testing components, and bringing the rocket together for launch. Here you can see the inside of the testing site, which is a shipping container that we lovingly call the bunker. The middle two are pictures of our fill system, which we use to flow gases and cryogenics into our tanks from outside the bunker. This past year, ATLO renovated the bunker, constructed a new stand to hold larger fuel tanks, conducted a burst test with structures, and conducted various types of engine tests with propulsion. Two of the most significant tests conducted were cold flows and hot fires. During cold flows, we test the engine at lower pressures and without ignition, while during hot fires, we use flight pressures and ignite the propellants. This year, we conducted the third hot fire of PT-163. Here you can see our engine during a hot fire. The engine is mounted to its test stand, secured to the shipping container by a large I-beam. To the left of the engine is our tank stand, which feeds propellant into the engine and prevents tank pressures from reaching dangerous levels. During this hot fire, we reached 2,650 pounds of thrust, breaking the collegiate thrust record. The image is so shaky because the test was a little more powerful than expected, and our camera mounting systems weren't prepared. However, this picture doesn't do hot fires justice. They are much more impressive when seen live on our YouTube channel, and even more so when seen in person. However, impressive images like that only come after days of preparation. Setting up for such a test involves moving materials to the bunker, integrating the engine and its avionics with the test stand, ensuring mission control is receiving information from the bunker, and handling high-pressure cryogenic systems, all while making sure that our members stay safe. As we move out of the design phase in the coming year, ATLO will become increasingly relevant, tackling projects such as vibration testing, cryogenic level sensing, active pressurization, testing of custom valves and the new engine, and many more. Among these projects is designing the high-pressure flight plumbing for TSM. This plumbing must first interface with ground equipment to prepare the rocket for flight. Quick disconnect mechanisms visible in both the intertank and helium bays must then detach the plumbing from the ground equipment. During flight, the plumbing delivers propellant to the engine and pressure into the tanks and valves. The plumbing system will also separate the nose cone from the rocket upon reaching a certain altitude. However, it also has to be lightweight, compact, and shock resilient. As you can tell, this is an incredibly difficult design task. Over the summer and the coming year, ATLO will tackle this challenge along with many others, doing our best to ensure that all hardware is tested and ready for flight as soon as possible. Jack will finish up with an overview of our timeline for the upcoming year.
Yep, so in conclusion, we're in the final 12 months before launch here, so that's pretty exciting times. We have a lot of things planned, but really by the end of the summer, we want to be done with most of our major design work. Around October, we want to have the first ignition test of our new engine, as well as test the avionics systems with it. And then in January, we want to do a full duration test for the engine. And then in April of next year, we want to do a full stack where we basically have the entire rocket fully stacked, and then we clamp it down to a pad and then fire it there. And that's the last checkup before we launch. That concludes our presentation. So first, big thanks to SEDS for putting this all together. We really appreciate it. It was a nice day. If you want to contact us, here's some information for our MASA social media and our website, as well as you can find our individual contact information on our website. If you're interested in joining, definitely reach out to us. And then on the next slide is a big thank you to all of our sponsors. Everything we do wouldn't be possible without the support of the University of Michigan, as well as all of our corporate sponsors. So thank you for that. And if you have any questions, ask away. Thanks again.
All right, thank you guys. In terms of questions, again, you can send them in through the chat. Are you guys able to see the chat, or do you need me to read them out?
Could you read them out?
Okay, yeah, sure. So the first question is, the slide showing the rocket body shows the use of physical/mechanical connectors to connect the different parts of the rocket. Are mechanical connectors more efficient than adhesives?
I'll let Jack answer that question.
Yeah, so for our rocket, you'll notice it's an all aluminum construction. So our tanks are aluminum, and the only thing separating a propellant is just one wall from the outside of the body of the rocket. We have to use mechanical connectors, and we can't use composites also because adhesives and composites start to delaminate at the speeds we're going. So we reach Mach 5 at burnout. So a lot of things start to break down at those speeds with the friction they experience with the air. So we're forced to use mechanical connectors, but that's a good question.
If I get to ask a question, why the name Tangerine Space Machine? I'm just very curious about the origin of this.
Actually, Jack or Paige, I feel like you would probably have like the best story about it.
I don't know, Paige, you want to talk about it? If not, I'll go.
Yeah, I can talk about it. It's a little less impressive than you think it would be, but we had a member shopping at the grocery store one day, perusing the craft beers section, when they came across the name of a Tangerine Space Machine by New Holland. Now, obviously, we're not going to endorse underage drinking or anything, but we all just thought it was a pretty fun name and pretty catchy, and we voted on it, and that was the name that won.
And we have cool logos with
Yes, we do.
Tangerine.
Our branding is very on point with it. Of all the questions we receive about the rocket, that is the most popular question, by the way.
I would imagine so. I've heard the name multiple times, as Blue, was planning to launch VX4 on the MASA rocket, and I was just like, Tangerine Space Machine?
Yeah.
That's not very maize and blue.
No, it is not. We are debating the color scheme of the rocket still, but we'll let you know.
All right. All right, there's a few other questions. Has MASA ever considered a plane-launched rocket mission, such as Virgin Orbit Launcher 1?
I don't know about the past, but maybe in the future. This is our biggest challenge yet, doing a single stage bipropellant liquid rocket. So we're always looking to do like the next big thing and to keep progressing. And we always want new challenges and to not just keep doing the same thing and to always push ourselves. So that's definitely something that we could look into the future.